I think we can start the seminar now, even though the audience is not big enough, but it's fine. So welcome everyone for joining today's seminar. The invited speaker for today is Tolu. Many of us already know about him and his research because he was one of the postdocs at our department a few years ago. And now he's an assistant professor at the Department of Earth and Environmental Science at the University of Rochester. Here he's back to present his recent progress in the research and to maintain some connection with folks at UMD, like he said. So let's hear and learn from him. Thank you.
Thank you very much, Grace. This talk, progress that we're making on this particular research question, imaging the bottom boundary of oceanic plates. And in particular, like I've mentioned, this is work that my PhD students and I have been focusing on, this particular challenging issue of extracting the structure of oceanic plates, conversions from the lithosphere, asthenosphere transition, while accommodating for of the sinking of sediments that contaminate our ability to extract structure in the lithosphere. So that's going to be the goal of my talk today. Some of you already know a lot about oceanic plates, oceanic structure, but I don't want to assume that you have a good grasp of the background. So I've kind of divided the talk into three parts. The first part will be some overview of what we know about oceanic plates for a general audience. So it will be seismology, but it will be seismology targeted at a general audience. And even within seismology, the constraints from seismology are varied. There are different techniques, different approaches, different resolution. So I will zone in on a particular type of constraints, that we get from using scattered converted waves. It's how these constraints from scattered or converted body waves help us evaluate models for oceanic lithospheric structure of the plates and its evolution. And my goal will be to try to convince you that these constraints lend great support for a particular type of model called elastically accommodated grain boundary sliding. At the end, you may or may not be convinced, but then I'll turn to a more particular issue, which is the issue I've titled the sinking of sediments. This is a particular critique of my work, my group's work, where some of our results were very critically reviewed, identifying sediment contamination as a possible issue in the interpretation of results from scattered waves. So three parts. The first part, general audience, general seismology, general marine geophysics. The second part, I will dive closely into this issue of models and what new constraints can tell us about the models of oceanic plate structure and evolution. And my hope is that you can stay with me for section 1 and section 2. But by the time I move to section 3, it'll be very, very technical. If I lose you along the way, that's understandable. So section 3 will be for those who are very excited about seismology and observational seismology and signal detection. But I will try still to make it as accessible to a general audience as possible. Now I can see all of you on that camera right there to my right. And so if you want to stop me at any point in the talk, ask questions or just give feedback, I can see you. Just yourself, grab my attention and ask your question. And I would very much prefer that this is more a conversation than just a one-way conversation. So let's start. The bottom of oceanic plates. We know from general plate tectonic theory that the structure of plates governs in a large degree the dynamics of our Earth. And the central tenet of plate tectonics is that the surface of our planet is broken up into stiff plates, and all the exciting action happens at the boundaries of plates, the surface boundary of plates, where one plate meets another plate, touches another plate, slides, builds stresses, creates earthquakes, volcanoes, and all the amazing dynamic activity on the surface of our planet. So the boundary, the lateral surface boundary of plates tells us a lot about the structure and dynamics of our planet. What is more challenging, though, is the unanswered question about where the boundary is within plates, across plates, as we transition from the plate, the lithosphere, the hard, rigid part of our plate, to the portion of the mantle called the asthenosphere, asthenos because it's weak, where most of the motion then is accommodated. So the question is, what is the boundary, the bottom boundary of plates? What is the transition from lithosphere to asthenosphere? What is its cause? And do our models fit what we know about plate generation, plate evolution, and the controlling factors of plate structure and evolution? Obviously, we have a model for what gives plates their strength, what gives lithosphere its strength, and what makes the mantle transition from strong, rigid lithosphere to weak asthenosphere. And the general simple idea is that it is temperature, right? So you have new plates being formed at a spreading center, at a mid-ocean ridge. You generate new crust, and then the plate cools. And as it cools, it gets stiffer, and the thickness of the lithosphere then evolves in that way. Now, with our general models of thermal isostasy, this simple view of plate structure and evolution being controlled by temperature is confirmed in topography of the seafloor. So this is a map of, and you see a half-space cooling model there, perfectly fits most of the topographical data. And there's some adjustment to that for older oceanic plates, but in general, half-space cooling model works pretty well. However, when we try to look at the bottom boundary of oceanic plates using seismology, we see differing views when we look at low resolution tomographic images that are either constrained from travel time or surface wave, and compare them to higher resolution views from scattered wave. And here then is just an average tomographic image showing that this idea of plate cooling, so you have low velocities at young oceans, and then the plate becomes kind of ages away and becomes faster, the velocities in the plate becomes faster, kind of fits with this thermal view. But if you look at the higher resolution body wave view, you see a lot of conversions. And so here again are just symbols showing the depth at which you have a particular conversion, a transition from high velocity to low velocity. And the question is, if you take all these results and you overlay them on a thermal model, half-space model, for example, how you can have conversions that seem to be at a temperature boundary, sometimes internal to the plate. You know, the question is a simple thermal model sufficient? And how do you explain these high resolution scattered wave constraints in the context of this simple thermal model? So the way to summarize that is you have a sharp velocity gradient across the lithosphere to asthenosphere transition, across the lithosphere to asthenosphere transition, in particular when looking at body waves. And trying to explain these constraints becomes the issue. I want to point out that there are different ways one can interrogate the transition from lithosphere to asthenosphere, in particular on oceans. On the left here, what you're looking at is an approach or a set of approaches or techniques that are looking at the oceanic plate structure while the seismometer is on land. So that triangle there is the seismometer, that star there is the earthquake, and using bounce waves, in this particular case, S waves that bounce off of the core, head back onto the surface and bounce back onto the receiver, you can interrogate the structure midway between the station, the seismometer, and the earthquake. So all these class of techniques, I will call them techniques where you're using a seismometer that is placed on land and interrogating the structure midway between the seismometer and the earthquake. This collection, this distribution of observation, huge population of that distribution comes from said observations here. There are different classes of observations that you can get where the seismometer, in the case of oceanic plates, the seismometer is placed on the seafloor, right? The seismometer is a submarine seismometer, and that's the triangle there. And you are using waves that are forward scattered or forward converted to interrogate some discontinuity underneath, directly underneath the seismometer. One might argue, and so here is a case, actually this is, in this case, so the black line is a P wave, a compression wave, the red line is a shear wave, and here you've got P and S conversions, S to P conversions. Regardless, one might argue that this type of technique where you're using converted waves from submarine seismometers potentially have the best resolution and potentially will provide us information on constraints on lithospheric structure. Keep that in mind because everything I will say in the third part of this lecture will be trying to improve constraints on oceanic plate structure by improving the quality of signal detection from submarine seismometers. Moving on. So about a decade ago or 2 decades ago now, no, about a decade ago, Kawakatsu and others did a very expensive experiment where you have here a borehole submarine station measuring earthquakes, detecting converted waves, and building this set of receiver functions. PRF, P receiver function, SRF, S receiver function. In any case, these receiver functions are signals of converted waves. If you look at this particular pulse here, that is the signature of a conversion from a transition from a high velocity mantle lid to a low velocity layer. And that red curve is their preferred model. And you can see from that red curve that there should be a sharp velocity gradient as you transition from a high velocity mantle lid to a low velocity layer. The challenge though is you need to explain that you need not just temperature. So this is what the geothermal will look like for say some old oceanic plate, that's the blue there. And if you try to translate this temperature to a velocity, the curves do not have a sharp velocity gradient. To go from blue to brown to yellow, you need something else. Hydration, partial melt, something like that to explain the seismic constraint. So you need a modification to our simple view that plates and their strength and their structure are governed primarily by temperature. So Kawakatsu depicted that in this picture. This, he says, is maybe the high school view of plates. And this is here, like he claimed, the graduate school view of plates. So on this side, you see the seismic velocities. You see this sharp change in velocities. And the question is then, how can you get this sharp velocity in his view? Some role for partial melt, some role for water, some role, but in our view, when I say our, my and my collaborators, we think just temperature and attenuation explains this rapid change in velocity without having to modify our understanding of how thermal gradients vary in the plates. So that's the setup. Go ahead.
Quick question. So when you describe the view by your collaborators, do you mean attenuation as the seismically observed attenuation, or the underlying mechanisms like partial melt or water or grain size?
Good question. Good question. So I don't mean the general view of attenuation. I mean a particular mechanism that I will explain in the next section of my talk. So stay tuned. Good question. It means you're with me. So stay tuned. So back to this issue of what's the model that we should use, and does that model require us to modify significantly what we know about a simple way plates should be formed and evolved? And here I've highlighted a couple of points that I think any good model should have. It should be simple. It should generalize. And these are my biases. It might be untrue, right? The Earth might not desire to be simple. The Earth might not desire to generalize. The Earth might be more complex. But in any case, my bias is that the model should be simple and generalized. The model should explain normal oceans. And more importantly, though, scientifically, models should be testable with new observations. And I'll proceed to summarize all cases of models into these two buckets. On bucket one, partial melt. This is one might argue is the view by a lot of practitioners in marine seismology and geophysics. And this is you can call it the underdog view, if you like. But the idea being that you can transition. So in the partial melt view, you can transition from a high velocity to a low velocity by adding a secondary phase, a secondary melt phase. The secondary melt phase has low rigidity. And so on aggregate, the rigidity will be lower, lending to the shear velocities a low velocity transition. If the transition is rapid from melt free to melt rich, you have that. You can explain that velocity. On the other hand, this is the attenuation view, Raj. The view that the structure, the rigidity of rocks, of aggregate rocks, will be influenced by the attenuation mechanism, in particular, what happens across grain boundaries. And because grain boundaries are weak, you can get a transition from high velocity to low velocity. In the lithosphere, the grain boundaries are strong, are rigid, they are locked. So that's the unrelaxed condition, and they transition to the grain boundaries become weak, either due to temperature, or water, or how fast you're forming the grain boundaries. And especially in that case, you can explain with this mechanism. You can explain the sharp velocity gradients in the oceanic plates. I'll point out though that these two models have a very distinct, unique prediction for what the electrical conductivity should look like, right? On the left, I'm showing you there the electrical conductivity that will be expected for the partial melt model, and for the elastically accommodated grain boundary sliding model, that might be what you will expect for its electrical conductivity. In some regime, in some cases, you might not even find changes in electrical conductivity while still being able to explain changes in seismic velocity. Not so for the partial melt. Whatever influences the velocities, however you influence the velocities by adding partial melt, you will also have to influence conductivity, because melt have a strong influence on electrical conductivity. Okay, and on the right here is a paper published a couple of years ago demonstrating what the prediction should look like for the evolution of the seismic velocities for the oceans, from young oceans to old oceans. So that line there that follows essentially the 1300 Kelvin geotherm is where we expect the depth of that seismically inferred high velocity, low velocity look like. And then outside from 80 million years out and onwards, the boundary there will then be controlled by changes in water content. So, we've got testable, go ahead.
I have a quick question for you. When you showed this prediction for the depth-age relationship for EAGBS,
yeah.
How much kind of leeway do we have on this in terms of the uncertainties on the mechanism itself? Are we talking about like 10 kilometers or?
Good question. I would say the simple answer is I really don't know. I don't know a lot about that, but I'll say we have so in terms of based on the experiments that were conducted, say, when was my paper published? Let's say 10, 15 years ago, I'd say probably plus or minus 10 kilometers. But these numbers are constrained by the activation energy and activation volume of this mechanism. Numbers that are still, uncertain, fiercely argued about. So they may change. Sometimes Shun and most mineral physicists always tell us, wait 5 years for all the arguments to die down before we know the precise numbers. So for example, Shun just published a paper very recently in JGR Solid Earth, where he's actually still trying to place constraint on the pressure effects for this mechanism. So, pressure effects, thermal effects, water effects, all these go into this Arrhenius law for how this the relaxation mechanism should work, may change those numbers. But I don't know now the status of those numbers.
Okay, so since your work, there hasn't been kind of a systematic look at the trade-offs between these different, or kind of the uncertainties due to these competing effects.
Mm-hmm.
Okay, just because I'm not familiar with the literature. Thank you.
Yeah. So as of now, that's of when we had those numbers, that's what they look like. We might write a review paper, in a year or two. Obviously, shouldn't be the head of that review paper, looking at those uncertainties. Yes. But if you are, I've not seen anything. If he finds, Shun is a very, honest scientist. If he finds something wrong, he tells me almost immediately, and he backtracks his own work. He's at a place in his career where he's not, he doesn't really have, he does the science, and wherever the science leads him, he goes. But great questions, thanks, Ved. And for the audience that's not very conversant with this, yes, the uncertainties in these predictions really come from the mineral physics experiments. And I might be able to get to that in a couple of slides. So the idea again is that attenuation, essentially energy loss when waves propagate through rocks, can explain velocity changes, velocity drops, and in particular can explain sharp velocity reduction. That's the story. Here is the idea of attenuation. Vibrating systems. A black system that's got no energy loss, no friction, will vibrate forever. Its amplitudes will not change. Leave it, it will vibrate continuously, undergoing simple harmonic motion like that forever. But then if you have a system like that blue system that somehow loses energy between one vibration to another, then the quality of vibration and the quality of that vibration is said to be not perfect, right? So the Q, the quality factor of the vibration, is a way to measure how much energy is lost. Inverse Q, attenuation, Q essentially is energy loss. And here I'm just giving you what the numbers look like for this particular oscillation, the blue oscillation. The blue oscillation has a QC of 3.3. In the Earth, the Q of, I think I might get this right or wrong, the Q of the lithosphere from PREM, 600 say, and then the Q of the asthenosphere, the low velocity layer, is about 18. And here is an actual physical model showing how you can damp off attenuation by having a viscous dashpot connected to a vibrating system. So this is how we come up with simple models of how attenuation might exist on our planet. And this is what we call a standard linear solid. If you take the standard linear solid and you aggregate it into a distribution of standard linear solid, you get the absorption band model. The absorption band model here is what we used in PREM, and the observations suggest that there is some frequency dependence to attenuation. Up here in this panel, shear velocity is velocity from the absorption band model, and that is attenuation that explains that drop in velocity. For standard linear solid, if there's one mechanism, one distinct unique mechanism for attenuation, if you cross from high attenuation, this hill, down to low attenuation, the valley, you can change velocities from high velocity to low velocity. Essentially, the velocity of the material depends on how far you are away from the attenuation peak, or how the frequency at which you are deforming the solid. I point out though, for the absorption band model, this Q-V relationship is not sharp enough, and the magnitude of those velocity drops are not enough to explain what we're seeing in the LAB without another attenuation mechanism. And that's this idea of elastically accommodated grain-boundary slide. So I'll explain it as briefly as I can using this illustration. So on the left here is a schematic of what might happen across a grain boundary. So on the top here is one grain and another grain beneath, and this shape is the shape of the grain boundary. You deform those two grains by applying a shear stress, and you will have the grain boundaries slip and accommodate that shear deformation with concentrations of normal stresses along the edges. Now, that will always happen regardless of the shape of the grain boundary. And the idea then being, in the short time scale, at some frequency, there will be a peak in attenuation. Essentially, if you deform the material at the activation time scale of the grain boundaries, there'll be maximum attenuation, and higher than that, there'll be high velocity. Beneath that, there'll be low velocities. And at lower frequencies, you get this absorption bound behavior that would then transition to a Maxwell body. Essentially, diffusion will smooth out the stresses on long time scales. And so that's the idea. As we've pointed out in the conversation with myself and Ved, this constraints on the details of this attenuation mechanism is still being studied in mineral physics experiments, in particular, the effects of grain size sensitivity, how much shear modulus reduction you have, and in particular, very difficult constraint, the influence of water. But we believe, right, that this mechanism is a valid mechanism. Here is a plot that I wrote back in the day of predictions from the this attenuation model. So here then what you're looking at is attenuation with depth. ABM is the absorption band model. ABM is absorption bound model. GBS is the grain boundary sliding mechanism. So if you include both mechanisms, you will get ocean plate age, and that peak in attenuation is coherent with the velocity drop. Note here, I've also included in the blue curve the attenuation model of Prem. So you're seeing that the velocity drop is really driven by the peak in attenuation over and above what is predicted by Prem. The question is, those are predictions. What does observation say? Obviously, these predictions are coming from mineral physics experiments and the theory, but what do observations say? And there are results coming online now that this peak in attenuation might be a plausible idea. So here are two authors, Takeuchi 2017 and Ma and Dalton from the Brown group. Where they are looking at here is the purple curve is the results after constraining shear attenuation using the seismic array somewhere in the Pacific. And to explain this peak in attenuation, as you can see, that's around 80 kilometers depth, they have to include our idea of a grain boundary sliding mechanism. So it seems, starting from say 2017 until about 2020, that this attenuation mechanism, evidence in results, new results coming online, bear it out. So that's the gist. But more importantly, how about that age dependence, right? So I'm gonna explain or present some results. These are results 3-4 years ago, showing, I'll argue, age dependence for normal oceans. Normal oceans here are oceans that are not perturbed by plumes or hotspots or things like that. So you'll see results from Shikoku Basin, Philippine Sea, Northwest Pacific, and the Northwest Pacific. This is not the experiment, but this is my last expedition into marine seismology. This is when I was on an ocean cruise, and going on a boat and dropping seismometers at the bottom of the sea is fun. I'm hoping my students can participate in it. But I just show this to point out that marine seismology is an expensive venture. To do it, takes a lot of investment, and oftentimes the quality of the data and the volume of the data is very small compared to what we have on land. But the Japanese have been very good at this. This is what an ocean bottom seismometer might look like, and this is a recovery of an ocean bottom seismometer after it sat on the seafloor, recording earthquakes and ambient noise vibrations. But often stations can only stay down there for a year and 2 months thereabouts. The Japanese did that for this experiment here. It's called the stagnant slab experiment, where some of the stations were recovered and dropped again in the same location. So good recovery of a lot of earth. So some of these, the color code is, I think the white ones are stations that were there for 2 years, and the black ones are stations that are there for 3 years. Essentially, they dropped the seismometer, went back, recovered, took out the data, dropped the same location. So great data.
Olo,
Go ahead.
Can you please come a little bit closer to the receiver? Because I have been a little bit trouble hearing you, like
Sorry about that.
for the past 2 minutes or something.
Can you guys hear me better?
Yeah, now it's better.
Okay, thanks. Please stop me if you cannot hear me.
Yeah.
Okay, so this is what the experiment looked like. But more importantly, my focus when we published this result was to look at age dependence. So essentially to see how the receiver function results, what the receiver function results tell us about structure when you're going from on transect AA compared to the orthogonal transects that should not vary so much with age. And that's the goal. Whatever signal I should show you, you should be watching out for how the structure varies from the transect AA compared to the orthogonal transects, say for example, BB, CC, DD, or EE. And here you see highlighting in the colors the variation of seafloor age, giving you a sense of how or what to control the structure of receiver functions when you begin to organize them or process them. Function of transects. Transect AA has most of the variation of ocean age, while the other transects not so much. The goal being to test the prediction of this age dependence for the elastically accommodated grain boundary sliding model. This is what the data looks like. This is spectacular data for marine seismology. This is what the data looks like. Here I'm highlighting what the data in the lower panel showing the seismogram, what the data looks like without doing any pre-processing. Notice that the horizontals, for those who often look at this, the horizontals are the RT seismograms. The horizontals have a lot of noise, in particular, long period noise. This looks like an infragravity wave passing through across the seismometer, right about when that earthquake was recorded. You high pass that infragravity wave and you can detect with good fidelity the onset of the earthquake, both on the vertical, the red seismogram, and the horizontals, the blue seismogram after processing. But again, already you see that doing submarine seismology is challenging. Before you do any kind of pre-processing, after you do any kind of pre-processing, that's the quality of the data. Decent amount of data, good data quality. What's happening to my, hope I'm not stuck again. Oh, oops, went out too fast. Okay, good. So this is what the receiver functions look like. At one particular station, one of my best station, that's station T06. Let me point out station T06 here. Yeah, right there, very close to the continent edge there, or the ocean island edge there, or island edge there. Distribution of earthquakes, one particular event. You take that event, that three channel recording, ZRT, vertical and horizontals, and you deconvolve the horizontals or the verticals from the horizontals, and out pops another trace. This is the trace we call a receiver function. So this is the processing, removing the verticals from the horizontals. The idea being that if you remove the verticals from the horizontals, you will normalize out the source signature and you will get the Earth's response. And so how you would read this image is this is delay time versus some spatial coordinate. The pulse at 0 is the direct arrival, and any other subsequent pulse following 0 time are conversions, where the sign, the signal of the pulse gives you a sense of whether you're having a velocity reversal, a velocity drop, or a velocity increase. And when we did this experiment, this pulse was clean, was clear, was beautiful, and that's what we inferred as the lithosphere, the transition from a lithosphere high mantle velocity lid to asthenosphere interior. We also did one better. Here again, you're looking at the receiver function traces as a function of back azimuth, essentially compass direction, north, back 036, northeast, southwest, all around the station. And if this conversion was a function of the texture of the rock, so anisotropy, there should be some harmonic behavior of the pulses as a function of back azimuth. And that's what these equations are expressing. You don't need to know the detail. The idea being if there was an anisotropy, significant anisotropy, coincident with the velocity reversal, when you do this decomposition from your radial and transverse to harmonic components, you should see significant signature on the harmonic components. Essentially, this trace is the constant trace, and the other traces, 2s and 2s, are harmonic behavior. Very little harmonic behavior is the story when we did this analysis. And this is a summary of our results. Again, point out AA, transect BB, transect CC, DDEE. And what we report is most of the variation in terms of age dependencies on the transect AA, not so much on the other transects. You summarize this. We summarize this in a plot like this: depth as a function of age, where the colors are our new results. And we think the summary idea is that we find age dependence. There are some stations that might be close to tectonic features that have changed over time, and that's what we're showing by these colors. But in general, age dependence in that old seafloor, it flattens out to 80 kilometers. So we think this is compelling evidence. Very little evidence for back azimuthal behavior. So we think this is not a function of texture or anisotropy, things like that in the oceanic lithosphere. So again, prediction matches, we think, to observation. And that's it. That's it for the state of, at least I think, using scattered waves, normal oceans, I think. Obviously, there are other people doing this work, but I want to point out in the next, say, 10, 20 minutes of my lecture, this particular critique. This is, I think, this particular critique in some ways is a growing up experience for me in terms of doing science. So this is what the looks like. This is the paper I just discussed a couple of slides ago. That's me and co-authors. And right after this paper was published, less than 2-3 weeks, there was a response by authors Calcatso and Abe, where they looked at our poster station, our very best station, where we have the cleanest, we think, data, and they showed this signal in the spectra. By the way, let me point out, what comes out now is very technical, is a lot of seismology, but I'll try to make it as interesting and as accessible as possible. But if it turns out I lose you, I totally understand. But to the seismologists in the audience, this is the spectra at station T06. Notice the repeating, and the colors, red, green, blue, red and green at the horizontals, blue at the verticals. You see that repeating spike, those repeating that seem to follow some predictable pattern. That is a signal of some kind of reverberation. And Calcatso and Abe suggest that all our results are, because the signature of reverberations, contaminated and should be taken with a grain of salt. Now that we've done some work on this, this behavior is similar to what will happen if you digitize, say, a soprano saxophone and you played some harmonic low C. You have all the harmonics show up in frequency. Essentially, the station, as it records earthquakes, is rattling. It's singing at predictable harmonic frequencies, and that was the last word of, in terms of my group working on this, until Evan, my PhD student, joined the group, and I tasked him with one of the most challenging projects, I think, to try to remove the singing of sediments. And so I'll give you a quick tour of what the singing of sediments look like and the work that has been done in the past. This is research that had been published in 1959, very well chronicled in this book, Mathematical Tour of Physics, I think, or something like that. But even scientists in this audience, Ved and his group, have applied techniques similar to this on land, where they're trying to remove sediment reverberations from receiver functions so that you can see better or extract better structure underneath the sediments. And this is how it works. So you have some input I, some signal I as a function of time. That is a function of earthquake convolved with Earth's response. And and that can be represented in the time domain and the frequency domain, as a function of omega. And these are other copies of that signal I delayed by some time t, or tau. So that's the delay time tau. So what happens when you're doing a marine experiment on the ocean is that you've got an incoming signal trapped inside this, in this case, water layer. And the subsequent arrivals on your seismograms are just carbon copies of the initial record, scaled by the reflection coefficient, water to solid, and delayed by this two-way travel time of the wave. And so when you go on your seismogram and you look for your output, your seismogram, all you will see is just a repeating copy of your incoming seismogram, scaled nonetheless, decaying nonetheless, but this signature, this trapped wave in the water in this case, makes it difficult to see any other thing, makes it difficult to see lithospheric conversions and any other conversion. And so this is what we're calling the reverberation effect, right? So if you take this output as a function of time and you try to write it as a series, this is what you will find for the reverberation effect. Essentially, again, a series of delayed copies modulated by that reflection coefficient. If you write it in the frequency domain, that is what it will look like. The question is, can we constrain this reverberation effect? And can we correct for it? Again, I said, this has been done on land before. And in our case, we think we can. In fact, we think we can do one better. We think we can constrain this reverberation effect, not necessarily from just doing processing on the signals, but from some a priori constraint on the reflection coefficient R and the delay time T. And this is what happens when you, because the reflection coefficient is less than 1, this series will converge in the frequency domain, and it will converge to this expression here, so that your marine data is just a scaled response. It's just a scaled in the frequency domain, it's just a scale by this filter. And so this is the singing effect. And that's Earth. If you can constrain the parameters of this singing effect, you can remove the singing effect. Note that the singing effect is just a function of the reflection coefficient R and the delay time tau. And this for us was like, oh, this was worked out for the water case. In fact, people know about this. The question we asked ourselves is, can we really build a matching de-reverberation filter that allows us to back out the sediment reverberations, to back out the water reverberations, and then to target the oceanic MOHO and LAB that's buried within our receiver function signature. Like I said, I walked you through the water case, but it's similar for the sediment case. Still a wave that is trapped in some waveguide, where the refraction coefficient being very strong is what traps the waves in that layer. And if you plot out that reverberation effect in the frequency domain, it looks like what? It looks like a comb filter. Well, I'm black, I've got black hair, I comb my hair, that's what it looks like. And the matching de-reverberation filter is just a matching notch filter that wipes out those strong reverberations at the appropriate frequency. The frequency behavior and the spacing of the filter, and the spacing of the combs, and the spacing of the notch is governed by the thickness of the sediment layer or the water column. But that's the general idea. So what did we do? We did a set of controlled experiments. This is what, for example, the structure of the ocean should look like for a submarine, a marine experiment, a water, a sediment, and then everything you really want to know, the thickness of the MOHO, the LAB, if you've got multiple MOHOs, things like that. And you're trying to really look for conversions from your MOHO or your LAB, but sadly, all these phases that I've highlighted in this image here are overwhelmed in general by those extra reverberations. So here is the receiver function original Earth response, the receiver function with that singing effect in it. Now we chose a structure where you can actually see the reverberations. The reverberations are just these copies, this negative, negative, positive, positive, and they go on and on and on and on. If you were to filter this receiver function at a short period, everything blurs together and all you will see is that singing behavior. When we apply the filter, the de-reverberation filter, we can mute, silence, remove a singing, and better see identify the conversions from the MOHO and the LAB that we're looking for, and we declare victory. Again, I point out that this is work by, Evan and I, and Evan did most of the analysis. Evan is sitting here in the lab, trying to actually write up revisions based on reviewer comments. So we've done the controlled experiments. Our goal was then to look at a normal oceanic mantle where we've got data, experiments, and apply this de-reverberation filter to the data to see if we can improve the quality of the receiver functions. And here in the next slide or two will be our results. Here is the raw seismogram after actually you do the high pass to remove the infragravity waves. And here is when you bandpass the seismogram, say at some frequency, I think just about higher than 1 hertz. Notice that the horizontals have this kind of beating phenomenon in them, so the radial and transverse. And that beating phenomenon is coherent on the radial and vertical, and I'll show you in a bit. But the idea being that this beating phenomenon is just this constructive interference of these waves that are trapped in the sediment layer. This is the spectra that bears witness to that reverberation. Again, notice the peaks. And here we've actually highlighted with a line the functional form of where those resonant frequencies should be as a function of structure, matching those resonance frequencies, giving us confidence that we have a good handle on the parameters of the de-reverberation filter. Not all the stations often express this resonance. Here, the resonance is again visibly expressed in the coherence between the Z, the vertical, and the radial, showing again as repeating patterns at the predicted resonant frequencies. So there is some detail to what sets up those resonance. We're actually not really completely sure why. Maybe topography, maybe the frequency content, we don't know. There's more research that needs to be done. But in any case, the resonance effect is borne out. We can predict it, we can model it, and we can build that filter. Notice that if you do a low pass on your earthquakes, you can actually remove that resonance. And so if you're just looking at long period waves, you can still do receiver functions on them in this particular case for no melt. But obviously you won't be able to see things like the MOHO or a sharp boundary or some thin melt layer. So doing this is very critical if you want to understand fine details in structure of oceanic plates. Okay, apply this filter to actual data. This is the original response without the de-reverberation filter. This is our receiver function after we deconvolve the singing effect. So before, after. Again, this is receiver functions. But in this case, they're plotted as times your direct pulse, and you'll be looking for all these conversions to PMS, BPMS, PSMS, BLS. They're very difficult to see. If you just sum all of that, all this receiver function, and look at their average, they look like an autocorrelation. This is one of the signatures of the singing behavior. After we deconvolve, we think we can see all the other phases. And then we can then model for their predicted timing and their move out to extract the thickness between the MOHO and the LAB. And that's what you're looking at here. This is before the filter. You see multiple peaks, no preference for a particular thickness. After filter, peak is more observable, and the phases will go into identifying the thickness, the MOHO to LAB. So this is really cool, we think. It's simple. Go ahead.
Quick question.
Yes.
So I see. So this is 0 at P. Is it aligned on P?
Yes, alignment on the direct P. Yeah.
Okay. So I'm just wondering what if you're choosing the reflection coefficient, what effect that has on the relative amplitude that you see on the right for the,
yes.
For the reverberation filter. Like how critical is it to get the right value?
Good questions. You guys are asking. Glad you're asking the right question.
That kind of like dictates how much confidence we should place on the detection. Right?
Yes, and that's, I think, again, this is a conversation. Same questions you've raised, same questions reviewers raised. Open question for more research. My guess is that because we are doing a notch filter, we're essentially knocking out frequencies. We have very, very strongly bias the amplitudes. So you're not going to be able to extract useful information on the amplitudes. But the relative amplitudes will be equally knocked out. And so this is useful for doing, say, timing. So that's why we are focusing more on the timing, stacking by timing, right? You will still see the peaks, but the amplitudes are a little wonky. But back to your question, yes, knocking out frequencies will affect the amplitudes. The amount of the reflection coefficient determines how far down into the floor, the signal flow that you're knocking out the frequency. If you guess the R's wrong, you knock too much and you'll affect the amplitude. But again, these are open questions, things we will explore in future studies. We think there are cool ways to kind of evaluate this issue. I hope that answers the question. If I've not, you can give me feedback.
Yep. For now, yes.
I have a question.
Go ahead, Ben.
On the left, where you say the original Earth response, this receiver function doesn't look very reverberative to me.
Indeed, it doesn't. What do you see?
Not much. I see maybe a phase around 1.5, 2 seconds. It's hard to say. There's not much. And so if it's not very reverberative, how do you pick the reverberation time? Because the way that we do it in Aaron's work is we compute the autocorrelation of the receiver function with itself, and then there's usually like a negative peak that tells you that there's like a reverberative.
You bet. Ben, your papers and the papers that came before yours, the song papers, were both a blessing and a curse. A blessing because you guys have done it before, and we thought just taking your approach, trying to do that autocorrelation will help us. It turns out it did not. Either because somehow this way of doing receiver function, where you're doing this multiple tapers, where we are down in coherent phases, somehow in some ways obscures those reverberations, I think. But more importantly, like you said, yes, it's hard for you. There is some like decaying autocorrelation behavior, but it's not strong. So taking your approach of doing that autocorrelation and trying to infer the parameters of the filter from the autocorrelation proved to be futile.
Oh, that's interesting.
That's why we went back to.
That has to do with with the way you construct the receiver functions.
Possibly.
That would be a really cool thing to follow up on, I think. I mean, it's a technical question, but we can share with you the way we compute the receiver function. You can compare for the same station if you do it with our approach versus your approach. You
bet. We are open to doing all and every suggested experiment to help us better understand why one approach succeeds, why the other doesn't. But great questions, Ved. But here is, I think, the elegant part of doing it this way is that if you've got a priori constraints on the sediment structure, velocity, thickness, you can build the filter. In fact, I would wager not strongly dependent, when we did some synthetic analysis, is not strongly dependent on that R value. It is more dependent on the delta T. Why? Because the R value has very little variation. It can go from, say, 0.9 to 0.7. You can't go much more than that. Reflection coefficients across sediment can't go very far. However, the thickness of the layer, and in fact, the strength of the conversion is what will govern this reversion filter. So I think, and this is what Evan is doing now, I think we can tune the filter without even doing much about structure. And that's what Evan is exploring. But great questions, Ved, and that's why we follow this approach.
Hey, Tolu, I have a quick question. So this is essentially on applying a comb filter to get rid of the resonance energy within the water column. And we do actually have, in Mars data from InSight, have like a very notorious resonance energy that we always wanted to get rid of. And I also myself use a comb filter for that. Do you understand, because the comb filters are so like sharp and stuff, is it any like filter effect that you have to worry about for using these type of filters?
Again, great questions. My guess is there is, and my guess is that my guess is that it would if you if you don't match the comb, so the notch is what you're trying to match the comb. If you don't match the comb, what you will do is you will distort the phasing of your whole receive function, essentially, and then you're out of luck. So you have to think about it that you're trying to match the notch to the comb, and the position of the comb. So that like valley, let me actually show you all. So that valley, this valley matched to the comb is what you're trying to do. But you're not doing it in an amplitude spectrum sense. You're doing it in a phase delay sense, right? And so if you don't match it almost perfectly, okay, that's my guess, you will just add phase distortions that will lead to incoherence in your receiver function. Back to the issue. How do you choose that? Again, I think Evan and I are trying to work out ideas, and I can share those ideas with you. I think is to try to tune it, to tune the filter, so play around with the parameters, looking for something you think you know about the structure of Mars. You know, so if you think you know something about the structure of Mars, that if you can predict, you will be confident about, in a Bayesian sense, in a grid search sense, whatever, then tune the filter, meaning just explore parameter space until you can match that prediction. That's the approach we've been thinking about. We've not implemented it for our data, but I would suggest that might work for you. What are your thoughts on that?
Thanks, Tolu. We can talk later. I guess you still have some more to.
No, this is it. I think this is it. This is just a summary slide. I can leave this up, but I think I've run out of time. I will take more questions if there are any. And thank you guys for all the feedback. Very, very, very helpful. And Evan is hearing most of the feedback. So he, again, big thumbs up to Evan. He joined me. This is the middle of his second year now, but he's been very productive and very successful, targeting a very difficult problem. I'm honored, privileged to be his advisor. Okay, I'll take questions.
Okay, so I have one more question on interpretation. So,
okay.
So your definition of the boundary where elastically accommodated grain boundary sliding will be an effect is driven primarily by the geotherm.
Yes. Right? Yes.
Have you thought about how variations in grain size might affect that? Because
yes.
if you look at Fowle and Jackson, for example, they
yes.
all they all explain the low velocity zone in terms of variations in grain size. They don't. So that is another mechanism apart from partial melt and temperature that is worth maybe looking at.
Very, 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 very correct, Raj. And very correct, Raj. We should explore that. Our bias, though, our view is that across that transition from a mantle, high velocity mantle lid to the asthenosphere, is that the grain size shouldn't vary that much. That's kind of our view. Now, are there independent constraints on grain size? I don't think so, but that's just our view. So our view is that grain size don't change that much. And when you look at the grain size sensitivity, whatever mechanism, like adsorption band model or the elastically accommodating grain band sliding, that's since the grain size, we think, again, there are no independent constraints, since we think those don't vary that much across the upper mantle for oceans, it becomes a little bit difficult for us to argue for changes in grain size being the driving factor. Now, regardless, if you have some mechanism for attenuation that has variations in grain size, they will potentially have that effect mapped into velocities. That's my opinion. Now we can talk about this more offline, maybe. Any other questions? Thanks, Raj.
Tolu, so the figure on the right, the red line is for your paper.
Yes,
I guess, how do you know the absolute VS from this kind of stuff?
we do not know.
Okay.
In all our study, we have used a priori velocities, either from previous work, from PREM, or from even ambient noise surface waves results published, average shear wave velocities published. And so our goal has just always to focus on the signature of the conversion from that velocity reversal right there, and to see if we can put constraints on the gradient. And to do that, obviously, you have to go to high frequencies, and that's been our goal: is how sharp, how deep, within error. Absolute velocity plus or minus 4 kilometers on the depth, on actually moving the depth back and forth. But the velocities won't vary on the order of 10% in terms of an absolute sense. That's kind of my approach. My approach was to, first of all, severe criticism by Calcatton and Abe, see if you can lay that criticism to rest definitively, and then look in particular at the sharpness of the LAB. That's been our approach, and we think that's a good approach.
So what was the result of this analysis? Was it that the reverberations are indeed important and you can get rid of them and then you get the same kind of LAB depths? Or...
Exactly. Raj,
okay.
repeat it.
Because I didn't get it. I didn't get, because that was not, to me, it was not clear by the end. Like, was that something that you...
If Raj, if they're not clear, let me repeat what you just said.
Okay.
We agree reverberations are important. We report that reverberations have been removed on land. We report that they are more difficult to remove in oceans, but we present a way to remove them. We apply it. It works. And we didn't gain so much, actually. Our structure stays within the ballpark of, at least for this region of the Pacific plates, what has been reported since the 90s, since the 90s. But I don't know, we can talk offline about perception, philosophy of how science is done, and how somebody may or may not be blackballed in the community based on, if somebody writes a paper about your work that seems to place a negative spin to your results, it seems to linger. And if you look at what do you call them now, review papers by Reichert, by Karen Fisher and others, if you go and look in detail, you find there 2 sentences, 3 sentences where this issue cast a negative light on our particular results, and we think this is a new result that suggests that we are going about doing this the right way. Okay, done.
Have patience.
Yeah, and don't worry about it. Controversy is great for citations.
Right?
I do have a question. I thought that Kawakatsu criticized the work in the Philippine plate, not the no-melt region.
Well, so again, back to the issue. Do we pick and choose what we criticize? I don't want to play that game. In any case, yes, you're right, Ved. But more importantly, this was not about actually the grain boundary sliding model or anything. This was really just about that particular issue, the signature and elimination of sediment reverberation from submarine receiver functions. And
did you try it on that data from the Philippines?
I'm not gonna do that.
Okay.
In fact, my group is not gonna do that. We will never. We'll look at new data. We'll present new results. And if somebody wants to go back and look at old data, they're perfectly welcome to do that. I don't think I'm gonna do that.
I have like another database question. So is there a way to, since we have more constraints on land and the sediment thicknesses in North America, for example, and also in the Yeah, they are pretty well known, right? They're well known to within like a kilometer or so.
Mhm.
So can you check your method on continental stations and see whether we can actually constrain sediment thicknesses based on the parameter fits that you're getting? Is there a way to constrain it?
Ved and Aaron did this in their work, and so the simple answer is yes. And
but can you do it with your approach? Can you do it with your approach?
Yeah, effectively, this is the same thing.
Okay.
The answer is yes, but there's nothing. I don't think there's, Ved and again Aaron have done this, and they've shown that it can be done. So the simple answer is yes, and Ved can talk to that if he wants to. Ved, can you talk to that? Speak to that a little bit.
Yeah, I mean, again, like you said, the precise timing is really important I think, in the reverberation removal. And while we do have good sediment thickness models, the velocity profiles within various basins are not at least easily found. I mean, they clearly exist because industry looks at all the basins, I guess, but so sometimes it's a little bit tricky. But we did find that when we look at the reverberation removal filter kind of characteristics, that they are compatible very nicely with the sediment thickness estimates for at least the the Atlantic coastal slope.
Yeah. Thanks, Ved. And Raj, the Earth will give you information, but it will not give you full information. Oftentimes there are trade-offs. And I said it's one parameter, right? It's one parameter, tau, delay time. So let me just move back and show you that illustration there of how you build that reverberation effect, right? It's one simple number, tau. It turns out it's not one simple number, right, Raj? That tau is a function of thickness and velocity, but also it's a function of the form of the velocity, the shape of the velocity within this layer, right? So in the water, it's kind of straightforward. It's just one number. In sediments, it's a little more complicated. It's how long that sediment has been there, the history of compaction, and if you've got maybe an exponential curve to the velocity or linear curve and things like that, which might make it difficult to, in an absolute sense, extract from that tau the useful information on the thickness of the sediments. Does that explain it?
Yeah, I mean, I get that. There's always trade-offs. I'm just wondering if one parameter can be better constrained than the other. And it seems to me that maybe to first order, the thicknesses maybe constrained better in some sense than the velocity profiles themselves. But yeah, it's interesting. Yeah. Thank you.
You're welcome, Raj.
Okay, is that it? That was a lovely discussion and a lovely presentation. Welcome, really, really welcome back, Tolu. And then I hope there are back and forth question and answer. I think there will be more collaboration going on. And then thanks everyone for attending the seminar today. It's already 12 minutes over, but I think we had a great time. And if you have more questions, please reach out to Tolu. And I hope to see you guys next time.
Thank you very much, Grace, for organizing this and inviting me. Thanks, Ved. Thanks, Raj. Thanks, everybody else. Thanks, Todd. Nice seeing you, Todd. Looking forward to hearing from you and seeing you when life returns to some kind of normal.